Hello again. This is the Pencrest High School AP Physics 1 video series. This is video 4D, Kepler's Laws of Planetary Motion. Now, Kepler was a Renaissance scientist and a contemporary of Newton, which means they were operating at the same time. He was primarily interested in mathematically modeling the motions of the planets. Planet actually means wanderer. It was observed, and it can still be observed, that the planets show up in a different place in the sky each night. They appear to move separately from the other stars. At least all the other stars appear to move together, sort of as a background. Kepler was an apprentice to a guy named Tycho Brahe. Tycho was an observational astronomer who had years worth of very precise data regarding the positions of the 5 planets that you can see without a telescope: Mercury, Venus, Mars, Jupiter, and Saturn. So the theory at the time was that the motions of the objects in the heavens were perfectly circular. Kepler tried to fit the existing data to a circular path model, but couldn't get it to work out right. So he started to use different models and finally hit on one that not only fit the existing data for the past, but also predicted the future positions of the planets with very remarkable accuracy and precision. Ultimately, Kepler formulated 3 laws of planetary motion that are still being used today. So first we'll look at Kepler's first law. Once he made the mental leap to the possibility that the orbits weren't circular, he tried a number of different mathematical models. And what he found was that when the orbits were assumed to be elliptical, the experimental data fit the models with a high degree of accuracy. So the law is stated this way. The orbits of the planets are elliptical, with the sun located at one focal point of the ellipse. So here you see a model of a planetary orbit. Here's the sun at one of the focal points. There's the other focal point, which doesn't have any physical significance. The ellipticity of this orbit has been exaggerated for clarity. The planet orbits are nearly circular, but not quite. They're just a little bit or slightly elliptical. There's a quantity that describes how elliptical the orbit is. It's called eccentricity. It's a pure number between 0 and 1. If we had an eccentricity of 0, that would indicate a perfectly circular orbit, and an eccentricity of 1 would indicate a straight line path. Well, not really a straight line, more of a parabolic or trajectory around the sun where the orbit isn't actually closed. So we'll be dealing with numbers between 0 and 1. The Earth's orbit eccentricity is 0.0167, very close to a perfect circle, but not quite. Most of the planets have very low eccentricities like this. There are objects that have highly eccentric, very squashed, very long and skinny orbits. We're going to look at those a little bit later. Now, the second law, as a planet moves through its orbit around the sun, because of the nature of the ellipse, the distance from the sun is changing. Kepler tried to determine the relationship between this distance and how fast the planet was moving in its orbit. He found that as the distance from the sun increases, the velocity decreases. So the farther away it is from the sun, the slower it actually moves. This is a very predictable quantitative change. If we draw an imaginary line from the sun to the planet, and as it moves from one place to another in a given time interval, we would say that the area swept out by this imaginary line is equal regardless of where it is in the orbit. So the picture probably helps more than the words. So when we look at this interval, say from A to B, and then this interval from C to D, and this interval from E to F, the time intervals are the same. So this might represent, depending on how far away the planet is from the sun, this might indicate a month or a week or a year, depending on how long the actual orbit is. We see that the velocities are different. We see that v1, when it's farthest away at the apogee of the orbit, v1 is the least or the smallest velocity. v2 is faster than v1 because the planet is closer to the sun. And then here, where it's the closest, from E to F, this velocity is the largest. The areas in each case, A1, this yellow wedge shaped, and this orange one, and this green pie shape, the areas are equal. So stated simply, the imaginary line drawn from the sun to a planet sweeps out an equal area in an equal time interval, regardless of the position of the orbit. So this is in a more mathematical sense. The times are equal, the areas are equal, but the velocity at 3 is faster than the velocity at 2, which is in turn faster than the velocity at 1. Now I want you to make a note of the extreme positions in the orbit. The closest approach is called the perigee or perihelion. That's down here. And the furthest point is called the apogee or the aphelion, and that's out here. Now, Kepler's third law, more of a strictly mathematical statement. There's a relationship between the mean radius or the average radius of a planet's orbit and its orbital period. This mean radius refers to the average distance from the sun, and of course we know the orbital period is how long it takes to go around the sun. Mathematically, we would say that k, the Kepler constant, equals r cubed over t squared. This Kepler constant is virtually the same for any object that orbits around the sun. R and t, of course, refer to the mean orbital radius or the average distance from the sun and the orbital period. The k is known as the Kepler constant, and its given value for the sun in units of meters and seconds is 3.35 times 10 to the 18th. It applies to any object that orbits the sun, including comets or asteroids, planets, anything else that's out there that actually orbits around the sun. Now, as it turns out, there's a Kepler constant for any given central body. In other words, any object that orbits, say, the Earth, like the Moon or a synthetic satellite, will display the same kind of relationship between orbital radius and orbital period, but the value of the constant is different because the Earth is now the central body. For the Earth as a central body, the Kepler constant is 1.02 times 10 to the 13th. Again, that's in meters cubed per second squared. Holds true for any object that orbits the Earth. There's another expression for Kepler's constant that depends not on the characteristics of the satellite, but on the mass of the central body. The derivation is in your notes. It amounts to the following. r cubed over t squared. This is the Kepler constant. Also equals big G, we know that, universal gravitational constant, times m2 over 4 pi squared. m2 is the mass of the central object. Okay, so that'll do it for Kepler's laws. Next up is planetary mechanics and highly eccentric orbits. Until then, enjoy. I'll see you again soon.